Good afternoon. My name is Charles Gillan. I work in Queen's University Belfast, as Brian has said. So if you don't know where that is, it's about 45 minutes across the Irish Sea from East Midlands Airport. I want to talk today about a project that we've been doing with the title here, Enabling Detection of Spice Adulteration with High-Performance Computing and AI. What this is about is enabling a small and medium enterprise through collaboration with the university using a HPC centre to potentially unlock new business. And it's all done using, as I say, AI. I thought it would be useful to put up the abstract just to set the scene. So we're talking about chemometrics in this talk. What is it? It's a tool in analytical chemistry, if you're not familiar with it. And traditionally it started with using statistical methods and now has evolved to include artificial intelligence, machine learning. In our case, it's about analysing spectral data. So these methods, AI methods, are now being used to complement the multivariate statistics methods. And I'm going to touch on one such multivariate method and look at one application of AI and how that has helped. And as I say, it's based around the work that we do in Northern Ireland in the Tier 2 HPC Centre. So I have colleagues here in the audience. I have colleagues who run the centre here to my right. And I also have the folks from the company, one person from the company, Stephanie, here on the left. A note about our sponsors. Kelvin, Lord Kelvin, William Thompson, was born in Belfast, hence we named the Tier 2 Centre after him. Not a lot of people know that, but there you go. Lord Kelvin was from Belfast. So the Northern Ireland HPC Centre came together essentially with EPSRC funding, so acknowledging EPSRC Tier 2 funding, from about 2019. Obviously we had a centre before. Some details are there. I'm not going to dwell on that today. Just to point out to you specifically the GPU capacity down there, and the work that I'll be reporting later has been using V100s, where this is a project that's continuing to develop and it's very much a work in progress. We'll be looking more at the A100s as we go forward. I should point out that Kelvin involves both universities in Northern Ireland, so the University of Ulster are partners along with Queen's. The work that I'm talking about is funded under the KTP programme of UKRI. It's through something which is all about knowledge transfer to small companies. So the company in this case is BA Analytical, which is about 10 people working in the area of detecting food fraud. So I'm going to tell you about the problem of food fraud, and that will lead us into the analysis of spectra. I'll talk, for the bulk of the talk is about analysing the spectra, and then we'll bring some conclusions together at the end. So food is food. We go to a supermarket or a store, we buy it. Well, it's a complex global supply chain, and there's a never-ending pressure on suppliers to reduce prices. And that goes all the way back to source. So food fraud, and colleagues in biosciences in Belfast are experts in that. I'm a computational physicist by training, so I'm more into the calculations. Food fraud is where the substance is modified for financial gain. Professor Chris Elliott wrote the government report on the horse meat scandal that those of you who live in the UK may remember. Chris is a leader at IGFS in Belfast, Global Food Security. You can find other papers if you Google Bansal and Singh. There have been cases about melamine in milk, etc., etc. The point here is that food fraud could occur anywhere in the chain, and we're going to talk about one specific example of that. Needless to say, detecting food fraud is very important, for many reasons, not just economic. So after you've finished hearing my talk, the next time you go to some coffee establishment and order a cappuccino and they say, would you like cinnamon on that? You'll maybe remember my talk because we're going to focus on cinnamon. I came into this not knowing much about food fraud, and I've learned quite a lot, and it's interesting. Cinnamon is one of the most highly valued spices. Well, that much I knew. And it comes from the bark of a tree, the cinnamomum. Okay. Turns out that that's mostly cultivated in Sri Lanka. And turns out that there are various potential advantages, nutritional advantages from cinnamon. So anti-diabetic, antioxidant, etc., etc. Lots of people will take a sprinkling of cinnamon every day. Now, one thing I learned about this subject is that they like powerful adjectives. So I'm going to talk now about the adulteration of cinnamon. It's quite a powerful word. I would have said contamination, but there you go. There's another type of tree called Cinnamomum cassia, or for the rest of my talk I'll just call it pure cassia. The cassia comes from places like China, etc. on the slide there. And if you grind up cassia and grind up cinnamon, they just look the same, essentially. Now, what's the issue with cassia? It's clearly coming from some related tree. Cassia contains a substance called coumarin, and it's estimated that around 6 grams of consumption of cassia per day over time is toxic to humans. If you look into it, it turns out coumarin does things like interfere with blood clotting and so on. So people who are perhaps compromised, taking anticoagulants and things like this, could potentially can have negative side effects by taking what they think is cinnamon and actually it's cassia. Cassia is cheaper to make. That's the point, that's the financial gain issue. Okay, let's start thinking about the chemistry of this. Now, this is a difficult slide to understand, so I'm going to talk through it slowly. If it's difficult to see, it's therefore hard for the computer to analyze. The blue line is the reflectance spectrum. So I'm talking for this purposes of this talk about infrared reflectance spectra. I'll explain why in a moment. The blue line is 100% pure cinnamon. The green line at the top is pure cassia. Now, if you look really, really closely, I'm going to step over and point this out. Really, really closely, you can see some shoulders on the spectrum in the green line. And those are the key that as a person looking at this with the Mark I human eyeball, we can pick that out. The lower line at the bottom is actually what's known as a spiked sample. And again, spike is quite an emotive word. What it means is that someone has taken a sample of cinnamon, mixed in some cassia to, in this case, 40%. And you see that the reflectance spectra looks very similar, but now you've got the cinnamon masked by the cassia, and maybe the shoulders aren't just so pronounced anymore. What can we do digitally with this information to see, can we use the machine to diagnose it for us? So we're going to use this spectroscopy, the reflectance spectroscopy. Why? So in the middle there is the machine from the lab in Belfast, one of them. It's a Fourier transform infrared instrument. Turns out the reason for this is that it's not cheap, but it's one of the cheaper instruments. On the other side of the lab from this, there are multiple mass spectrometers. And the mass spectrometers are much bigger beasts, much more expensive to operate. But the important point I learned going in, initially I thought, the molecule's the key. Turns out, when we're analysing a sample like you see here on the right of the brown powder, it's not just the cinnamon molecules themselves. It's all the other things that go together when you are growing this in an environment. So the soil will have chemicals in it that eventually get absorbed. So it's not just about being able to identify a single batch of cinnamon. It's about the fact that these are mixed together. So therefore you have multiple samples of cinnamon that you have to train. I'm preempting what I'm going to say. Fourier transform infrared is manageable. There are efforts afoot to make it portable. But of course, you could go back to the lab and start using things like Raman and mass spectrometry. But that's not the purpose of this talk. So, like in other areas of computational science, we're going to need to pre-process the data in some way. It's part of the multivariate process. It's also part of the machine learning process. This step is common. What we want to try to do is to remove artifacts due to the measuring process, perhaps, and thereby enhance the prediction performance. Now, we spent a very long time working with different types of methods. Today, for the purposes of this talk, I'm just going to mention standard normal variate. We found this to be sufficient for now, but I say we could say a lot more about it, and I know Stephanie, who did all the work, can talk at length about that. So just standard normal variate is defined with a mean and standard deviation like this. So we convert to scores called Z scores. You might look at that and say, but they're exactly the same, and actually looking at them, they're exactly the same. But the key thing is that compared to the reflectance spectrum, which has essentially an arbitrary unit, we're now normalizing things into a much different range of numbers, which is suitable for our floating point calculations on the chip. Sorry, that's the other way around. That's the raw spectra, and then it's normalized into a smaller range. So what did we do for multivariate analysis? Well, again, we're going to just talk about principal component analysis here. We have data on many other calculations, but PCA, fairly well known, unsupervised learning technique, hopefully brings together clusters of information when you look at your principal components. Doesn't discard any samples or characteristics, so we use the full set. And as the name principle implies, it's about minimizing the dimensions in the data. So typically a spectrum would have anything up to 1,500 points, 1,500 frequencies of measurement. So what did we do? We considered pure cinnamon samples, we considered pure cassia samples, and then we had mixed samples. So we have three types, three classes, three groups, if you like. What we also considered was pure cinnamon, and then the other two groups together, so pure cassia and mixed cinnamon cassia as the adulterant class, and the pure class was cinnamon. So we did a two-class model and a three-class model. Now this could be run, it was run on Kelvin actually, but it was not so computationally intensive actually. We were able to do this using R, the R package, well known in the statistics community. And we were calculating different types of distances. So what did we get there? So let's look at these two sets of calculations. The two-class model here on this side of the screen, you can see from the dots the adulterant and the authentic are really mixed, making it very difficult to use this to do any sort of predictive analysis. If you look at the 3-class case where we had pure cassia as well as adulterated as well as pure cinnamon, it looks even more complex and intermixed. So we have little success using the PCA method. We also looked at partial least squares discriminant analysis, and it wasn't any better. So, as the talk suggests, we turned to machine learning. So, we found that the key point was the hyperparameter search, and that's where we needed a tier 2 center. We also found that float 64 was essential for machine learning. We had to use that to be able to reach the conclusions that you're going to see. I'll talk about samples in a moment. So we're doing all this with scikit-learn and TensorFlow. We didn't have to develop software for the machine learning. We had to develop the driver code to call these, of course. Now, you will say to me, obviously looking at that, but hold on, Charles, there's only 186 samples. And I'd say, absolutely. This is something that we are developing, is getting more and more samples together from the instrument. So what I'm reporting is, you might say to me, well, actually, that's maybe not so good. But what I report is optimistic in showing that we can do an analysis with this number of samples. So we used about 130 samples to train the neural nets, and we used 56 models then for the validation runs, which is about a 70-30 split. I show this not for you to dwell on the detail, but to show you that we used TensorFlow. This is one of the outputs you can get when you print the model. We used multi-layer perceptron with a dropout layer. This is the 2-layer case. So you have your input layer, your output layer. This is the case where we had pure and adulterated 2 outputs. In the middle, we did lots and lots of calculations where we changed the number of nodes. And then we did this all again with 4 layers. Fairly standard things to do. Our processing pipeline, which is constructed in bash scripts with Python code then, is again relatively traditional. We have data preparation, build and train models, validate models. Within that, within the data preparation stage, we obviously have the data scaling, which I've mentioned. Standard normal variate worked pretty well. We do different random choices. We obviously use crossfold and so on, and test this out by making random choices for our 70-30 split. Then we do the model training, and you'll see the length of time required in a moment. We do that over a whole range of hyperparameters, and to say again, this is why Kelvin became so useful to us. We haven't quite got as far as running Horovod yet, but earlier this morning, Professor Panda mentioned Horovod. That will be something that we hope to do in the near future to parallelize this work even further. We focused on using a V100, so TensorFlow GPU. We find that works very well. We find that the GPU is really essential over using CPU mode for this. And then the testing and results at the end. So we have used obviously a sigmoid for the output classification. We need to use one-hot encoding. You'll see that come up in a moment. So let's just look first of all at what happens if you do the calculations with our sample set and we simply do true cinnamon versus, in fact there's a mistake here, that should say adulterated. I'm sorry, this version should say adulterated. It's both pure cassia and spiked. So 32 samples of true cinnamon were calculated as true cinnamon, predicted to be true cinnamon. However, 2 samples of true cinnamon were predicted to be adulterated. And then here, 1 sample of adulterated was predicted as true cinnamon, and 20 samples of adulterated were predicted as adulterated. So all in all, we were approaching a 95% reliability rate with the best model. So then we went to the three class model, where now we distinguish true cinnamon, pure cassia, and spiked mixtures. You can see things are okay, but there's still work to be done. True cinnamon was correctly diagnosed 26 times in the set, but there were some samples that were incorrectly predicted as being cassia and spikes. And with cassia, we did maybe not so well in this case, that we predicted some pure cassia to be cinnamon. So there is work to be done. So then what we did was we said, okay, let's break out the different percentage spiking. So we have 10% cassia in cinnamon, 20%, 30%, 40%, and 50%. This is where the one-hot encoding came into the picture. And again, things aren't as perfect as they might be. True cinnamon, 17 times correct, but notice that 20% spiked cinnamon, so 20% cassia in cinnamon is being predicted incorrectly as true cinnamon. If you're interested in this, talk to us offline, because we have some background information on what we think has been happening with the mixture preparation that might do that. Interestingly, the spiked cases did a little bit better. So, why did we need Kelvin? What was the actual resource consumption to make this happen? The work was proven, as it were, on a single CPU with one task on a small laptop. The code was debugged, but then moved to the Kelvin system. The runtime to do the model training, when we had 2 classes, was in the region of 2 hours, and you can see the memory going into the gigabyte range. Again, that's partly because of the way TensorFlow, if you know it, maps all the GPU memory. Took me easily 2 weeks to figure out why I couldn't get my code to run, because I hadn't asked for enough memory in the batch queue, that you need to allocate enough memory on the CPU to match the GPU. When we start adding classes, it's very noticeable that the training time increases. Now, if we start adding more and more samples, which is the aim here, those times will obviously increase proportionately. So 8 hours for 3 classes, and when we got to 7 classes with the one-hot encoding, that was 18 hours. And that's CPU and GPU. So principally running TensorFlow on the GPU. We let it partition the work as it wishes. So what can we conclude? It turns out cinnamon and cassia is one of the more difficult spice cases. Things like sage and rosemary and other spices for which there is data are easier, not saying they're easy, but easier because the spectra are not so similar. So the cinnamon cassia case is different. The PCA didn't do terribly well. We're doing better, but not perfect. So neural networks have performed a lot better, but you can see that it's taking a lot more computation time. And that's where the HPC Center has come in to its own. This has been very helpful for the small company because they would not have access to that resource themselves. Okay, you could argue that they could buy the cloud resource to do it. I would say we in the university are using these tools, TensorFlow, etc., continuously on many projects. So the environment is set up and tuned and ready. There's no setup cost for that. And clearly you may say, well, why didn't you do convolutional neural networks which potentially add value when we're doing this kind of pattern classification? And the answer is absolutely, it's work in progress. We're doing that. So that's the end of my talk, and I hope that I haven't put you off asking for cinnamon in your cappuccino. And I'm happy to take questions.